Most of the videos I put out are overviews of how I make parts on the PM30, and I've been getting some questions recently on how I model them in 3D before that. This isn't going to be a get started with modeling in SolidWorks video, but I'll talk generally about the approach I use when copying existing parts in SolidWorks. A lot of people would consider a fully complete 3D model a waste of time, but I've learned the hard way it's worth the additional upfront effort. Angle grinders are amazing tools, and work gets done a lot faster when you don't have to use one. So in this video, we're going to model this utility pump in 3D so we can use it in an assembly. The next 7 minutes are going to be this kind of over-the-shoulder view and me discussing my process and mistakes when modeling this pump in 4 times speed. Alright, so everything starts with a sketch, and I thought that the kind of most identifiable or maybe easily measurable feature on the pump was this fan cap. That's the cap at the end of the motor that the fan sits under to cool, to kind of pass air over the fins. And I started with an extrude, putting some chamfers on it. Here I'm making that indent where the intake is. You can't really see it in this shot, but you'll see I started with an extrude and I keep going with extrudes. And anytime you're modeling something where you're kind of extruding on top of an extrusion on top of an extrusion, it's usually a pretty clear sign you should have done a revolved feature, if it's like a kind of cylindrical shape like this anyway. But that's how I started, and kind of the technique I use. Just with most things, I guess in 3D, there's multiple ways, many ways to do the same thing. And this is where I started and kind of ended up with. So here I'm modeling the first fin. And what I really like to do is kind of step back and look at the part that you're copying and try to identify patterns, because patterns and revolved features will be your best friend. So there you saw I only modeled one fin, and now I patterned them in a line. And then I did a circular pattern, skipping the instance at the bottom, because that's where the kind of junction box, I guess, or the electrical box of the motor, excuse me, is going to sit. So here I'm sort of taking up that top face, and again, that's just eyeballing. Like, the main goal here for me most times when I model something is to put it in an assembly and see if things interfere. So I know there's nothing in it that's going to be right beside the motor, so I'm not particularly worried, with every millimeter. There's certain things that are more critical, like the hole spacing, let's say, for the mounting, which will come in a little bit here. But, how far exactly the junction box sticks out, or, how accurate the fans are. Like, if you look at that motor closely, those fins are not exactly what's on the motor, but it's good enough. It's just kind of like an appearance thing. So here we're modeling the, I guess, sort of the base plate of where the motor meets the pump, and the feet. And if you pay attention closely here, you see I made a mistake here on modeling the feet. I didn't have the motor in 3D in the same orientation as the motor on the table, and I got kind of confused. So I'm starting again here, modeling the feet. But here's a pattern, right? We have 2 of those feet. We know they're going to be the same. So I make one of them and I keep it as a body. I don't merge result. One of the mistakes I made for a really long time was always merging the result when you do an extruded boss in SolidWorks. And that's not such a good idea, because it can be more difficult to pattern, and you can always merge separate bodies at the end, which is normally sort of what I stick to. So here I'm measuring the hole spacing, which is critical. And one little trick that you may not know with SolidWorks is, if you want a dimension to the edge of a circle, not the center of a circle, you hold shift while you're clicking on the side of that circle and drag it towards a center line or another circle or whatever, like you see there. And specifically with modeling things that already exist in front of you that you're measuring with a set of calipers, this dimensioning to the edge of a circle is really helpful, because when you're measuring with calipers, it's not so easy to kind of put your caliper on the dead center of a hole, but it's real easy to measure the size of that hole and then kind of the spacing between that hole and another one, kind of to their edges. So that's a trick I use all the time when modeling. And if you don't know about it, it takes a real kind of roundabout way of putting on sketch relations and tangent lines and things. So this saves a lot of time. Here I'm just measuring the junction box, pretty easy, measuring the spacing between the junction box and kind of that pump mounting flange. And again, you kind of see me looking at the motor from a few different angles doing this, because I'm really just eyeballing here. This isn't, super exact. I know I've got many inches between the motor and the next thing on the side of the junction box, so this is kind of just getting it in the ballpark, let's say. All right, so the electrical motor is pretty well modeled, and here I'm starting to model the pump side of this thing. So again, here you can see I'm dealing with another pattern. I'm only modeling half of the flange, and I'm going to mirror the sketch to make the other half. So we're measuring the flange thickness, and then here you can see I almost made the same mistake of going with an extrude for the pump body, but you can see there it kind of necks in twice, and here I got a little smart and went to a revolve feature instead of an extrude on an extrude on an extrude, let's say. Ballparking most of these dimensions, okay, the length is important, so I want to make sure that the overall length of the motor is accurate. But these little steps, you don't really have to be so accurate. There you can see a sketch getting a little squirrely on me, which does happen. But mostly with those steps, I can't get my calipers. They're not kind of long enough to get to every single feature. But I just do, I'm drawing what I sort of think this looks like. I'm looking at the steps and making mental notes kind of how big they are, because they're not really that important. You're going to see in the assembly a little later that there's nothing really around it. So this is mostly, these things are aesthetic, and the important thing, so these ports are important. Which port is the intake and which is the pressure side is important. These are 1/8 1 inch NPT ports. Their positions, their relative positions are important. Here we're doing some cosmetic fillets, and it's starting to look pretty good here. So we got to still put in the 1 inch NPT tapered threads. So I go to the hole wizard, select the taper threads, select ANSI inch, and select your size, so 1 inch. And I also, this is sort of just force the habit from the first design job I had. The company had internal standards to make every threaded hole purple, so I kind of stuck with me. And it is helpful when you're kind of stepping back and looking at a model to know what's a clearance hole and what's a threaded hole. Adding the colors. In this over-the-shoulder view, the motor looks orange, but it isn't, it's red. And here we are putting in the cable entry to the junction box. Now, if this seems like overkill, it's actually quite helpful. Not knowing where the cable's coming in and out, you can run into routing issues. Like, let's say you put this thing beside a wall where you don't have access to the cable. That's not going to work. So I like to just put a little stub that shows me when I step back and look at the assembly, I know exactly where the cable's coming out of and kind of where it's got to go. And it's pretty much done here. So I'm just looking around, make sure I didn't miss anything major. We drop down to the real view graphics to make the part look a little prettier. It looks really nice, but I generally don't model with this setting on because it can slow down the system when you're dealing with larger components or assemblies. But yeah, this is pretty much it. So this model will give me enough confidence to make sure that I'm not going to interfere with something, and I know I can put it in an assembly and confidently model around it without really being worried that something's going to get in the way. I know where the cable is leaving, and okay, so here I'm putting in a little bit of extra information, which is which port is the intake port, which is the pressure side. I like to label things like this so I can just see it quickly in the assembly, make sure that I'm doing all my routing correctly. And you mess something like this up and it does really suck if you think the intake side is the pressure side. So don't forget to make little notes like that for yourself. And so this is that pump in its kind of final resting place in the subassembly, in the routing subassembly of the coolant system that I'm kind of kicking the tires on as the next upgrade for the PM30MV. I really want to do a spindle upgrade, but there's a bunch of things if I'm going to do that I got to do first, one of which is a more sturdy base. And if I'm going to design a more sturdy base, I might as well design it with some provisions for a flood coolant system, which is what this is here. And directly to the right of the mill, you see the base I'm currently using, which is the original Precision Matthews base on these outrigger legs that I designed and made that I thought would help the rigidity issue, but it didn't. It was a band-aid solution at best. So anyway, here you can see the pump motor with enough detail to give you some confidence that everything you're going to put in is going to fit nicely and nothing's going to interfere. So the general concept of the flood coolant system is pretty simple. I've got this suction strainer down here that sits in the reservoir. It'll bring fluid to the intake side of the pump through this quick disconnect that'll let me take off every component that's selected blue here because it'll be sitting in the bin, so I can't pull the bin out if that arm is on. There's a quick disconnect that'll let me disconnect that arm. And then the pressure side goes through these clear hoses through a T, out through a ball valve, through a whole house water filter, and finally to a solenoid that'll control flood coolant coming to to the spindle. The first T, I've got a ball valve here, which will let me meter how much goes back to tank. Then I've got another ball valve to meter the pressure that will go to to the spindle. These two pressure gauges will give me some indication of how dirty the that whole house water filter is and if it needs to be changed. Then on the very left side here, there's a solenoid valve that'll be fired by the CNC controller to, you know, turn coolant on and off when machining. And so this is kind of the pressure side of the flood coolant system I'm thinking about. I didn't come up with the design myself. I got it from CNC Cookbook, pretty much copied it 1-to-1 to fit in this to fit into this base. And yeah, there's still a lot more work to be done, like designing the enclosure and the kind of drainage and return side of the coolant, which will come through the top of the enclosure or the bottom of the enclosure. And yeah, I have no idea if this video was useful, but I hope you guys enjoyed it anyway. Thanks for watching. See you later.